Okay, and it's really important that we can work out what the possible error is in our calculations as well. So I'm going to use the same example I used in the previous video, which I filled out the table based on that. So this is the value that we worked out for y when x equals 0.5, and the question is, what's the most that it could be out by? When we've done these little steps that have tried to follow the function along, what's the worst possible case that we could be out by? That's really, really important that whenever you do a numerical calculation, you work out the maximum error which you could be faced with. And here's a formula for finding the maximum error for Euler's method. So h is just the increment step, so that's what I was calling delta x previously. So effectively this column is h as well as delta x, and we need the second derivative of the function. Okay, so here's my first derivative that I used to work out all these businesses. So this was effectively the f of yx was the first derivative. So now I need a second derivative, and if I differentiate this thing again with regards to x, I just get negative 2. So in this kind of straightforward example, the second derivative is just negative 2 all the way down, and that won't always be the case. It's a constant, because if this was, say, x squared, then this would still have x in it, and it would depend on the value of x. So this is a relatively straightforward one. And then we have to bung that into our formula. So this is the formula. So h in this case is a constant, and y dash is also a constant. So this is just going to be a constant. So what have we got? H squared will be 0.01 times negative 2 will be negative 0.02 divided by 2, 0.01. And in this case, because the second derivative is constant, this will be the same all the way down, but that won't necessarily be the case. Okay, now the E sum means that we need to sum the errors as we go along. So after one step, the most we can possibly be out by is 0.01. Okay, and then we could be out by another 0.01 in the second step. So the worst case we could be out by is 0.02. So what you're doing is taking the absolute value of these things and adding them on in each case. So it just goes to adding on an extra 0.01 each time. Okay, so the worst possible case when x is equal to 0.05, I need to go one more step, don't I? Okay, so when x is 0.5, we worked out before that the y value, so the y value when x is 0.5 is negative 0.7715, but that 15 is really sucked up by the error bound plus or minus 0.06. Okay, so there's enough of a significant error that the third and fourth decimal places there are actually fairly meaningless. Okay, so whenever you do a numerical calculation, it's important that you're aware of the possible errors which have been introduced.